should know the concentration of the charge carriers. As we said, there are two types of charge carriers in semiconductors. One is electron, and the other are called holes, right? So, how many holes are there per unit volume of the semiconductor? How many electrons are there per unit volume of the semiconductors? We should know that the concentration of the charge carriers, right? Before this topic, we did the Fermi-Dirac distribution because uh, uh, electrons are Fermi particles, so we should apply the Fermi-Dirac distribution to know how they occupy different energy levels. And before that, we did the density of states. Like, if you remember, I told you uh, in physical classes, in probably the last couple of classes, that these density of states like chair, they are like chairs in a hall, right? Chairs arranged in a hall. And we are suppose people, so how people try to occupy those chairs, right? In fundamental particles, we have uh, like, if you remember from your statistical mechanics, we have for particles to occupy states, right? There are three kinds like Boltzmann distribution, Boltzmann particles, and Fermi-Dirac particles, and Bose-Einstein particle. We call it bosons, right? So here, how the charged particles will occupy those states, like people sitting on chairs in a hall, right? So that is governed by the Fermi-Dirac distribution. Right? What is the density of states? We know from the last time discussion that the density of states in the valence band and the conduction band is proportional to the square root of the difference of energy, right? The density of states mean the chairs, the availability of chairs. There is no chair in the band gap. Remember, there is no chair in the band gap. There is no state in the band gap, right? So we said last time that density of states, right? In the conduction and valence band, right? If this is the valence band and then is the conduction band, right? So there will be no states here. There are no states here in the band gap. There are no chairs for people to sit in, right? However, there are states, the conduction band, and there are allowed states in the valence band, right? And those states, the density, their density increases as square root of energy. Right? It was like this. Square root function is something like that. Similarly, in the valence band, right? The density of states for holes was like that. Something like that, right? So the density of states in the valence band was equal to 4 pi, right, to mn star T over 2 E minus E
सर दिख नहीं रहा सर
and
राइट पे लिखेंगे सर
say it again.
सर मैं कह रहा हूँ राइट पे लिख ले सर और लेफ्ट में दिख नहीं रहा
राइट पे लिखो इस
यस सर
साइड पे
बोर्ड के राइट साइड यस सर इस साइड पे लिख ले सर
और ये बोर्ड is the board visible in the frame? Is it coming in the frame?
Yes, sir.
फ्रेम में नहीं आ रहा?
Yes, sir. Visible.
नोट सर
मेरे पास तो आ रहा है,
सर
आपकी अपनी
सर नहीं आ रहा, हमारे पास नहीं आ रहा, सिर्फ
सर विजिबल है।
हाईलाइट दिखा है।
हाँ?
Visible है सर.
आपके अपने उसका प्रॉब्लम होगा। So there might be problem with your
ओके सर।
own video system. How is it now? Should I turn on all the lights or not? ये बेहतर है या पहले वाला बेहतर था? मैंने अभी 2 लाइट्स ऑफ की, फ्रंट में थी।
सर राइट साइड पे लेके लेफ्ट साइड पे ना लेके वहां पे नजर नहीं आ रहा।
Sorry, say it again.
सर लेफ्ट साइड पे ना लेके राइट साइड पे लेके।
लेफ्ट साइड पे क्यों ना लिखूं?
सर हाफ बोर्ड नजर आ रहा है, हाफ नहीं आ रहा है, इस वजह से।
ये आपकी उसका वीडियो का फर्क होगा, आपके अपनी वीडियो सेटिंग्स का फर्क होगा। मेरे पास ठीक है, बाकी लोगों का क्या है? बोर्ड, सारा बोर्ड आपके पास विजिबल नहीं है। कितने लोगों के पास विजिबल है? एक पर्सन के पास सारा बोर्ड विजिबल है कि नहीं?
لك chapter بتا سر جوا سم بورد نستم نخكاري
सर बोर्ड नखकारी लिंक नखकारी
हाँ?
لك دي chapter بتا وسم دا بورد نخكاري سر جي
داسې کسان شته چې هغې سره ټول ښکاري. ما سره خو دلته فریم کې راځي که نه.
सर रोज पूरा ښکاري.
ها؟
बस फुल
وس
ښکاري
ايشو سر جي وس ايشو ايشو
فل دی، اوس صحیح دی.
ٹھیک شو
او look, should I turn off the lights or not?
सर ब्लर راته ښکاري لیکل خو نه ښکاري سر.
लाइट सर صفا शो, नूर को खराब शो.
सर क्लियर दे सर.
सर वो सही शो बिल्कुल नखकारी.
Okay, so that is the density of states in the conduction band, and that is in the valence band, right? That is the conduction. The first one is the conduction band. This one is the valence band, right? It was 4 pi 2 MPhil star and EV minus E, right? These are the density of states. These are the kind of chairs that are available to you, right? Now, how people sit on it, right? इस इन लोगों की क्या वो है, तबीयत कैसी है, कैसे वो ऑक्यूपाई करते हैं. That is given by the Fermi-Dirac distribution, right? The probability of occupation, and we know that the probability of occupation, right, function was equal to 1 over 1 plus e to the power e minus e f over kt, right? Basically, this is the probability of occupation, which shows the characteristic of the particles to occupy a certain level. लोगों की तबीयत को जांचने का ये इक्वेशन है. ये ऐसे लोग हैं, इन लोगों की तबीयत ये है, राइट, कि ये सबसे आगे बैठते हैं, फॉर एग्जाम्पल, right? So this gives you what is the nature of the particles, how they occupy those states, and these are the states. Now, what is the distribution? Now we can find the distribution. आप इसको जितने आपके पास चेयर है और जितनी उनकी ऑक्यूपेशन प्रोबेबिलिटी है, तबीयत है, उनको आप मल्टीप्लाई करें एक दूसरे के साथ, तो आपको पता चल जाएगा how many chairs are filled, and that will mean that how many people are there, right? So how many particles are there? So that is, we call it the distribution, right? So the equilibrium concentration, the equilibrium concentration of electrons. Right? How much is the number of electrons per unit volume? Right? Equilibrium means there is no temperature gradient. Equilibrium means no temperature gradient. No temperature gradient. Equilibrium means there is no temperature gradient. There is no potential gradient. कोई feel नहीं है. Equilibrium means there is no potential difference. There is no temperature difference, right? So in this situation, we will call it they are in equilibrium. कोई force नहीं है. There is no force on the electrons that they can be just pulled to one side or to another side. It is in equilibrium. There is no temperature gradient. Like one, it is not like one side of the semiconductor is hot and the other is cold. No. All the semiconductor, whatever sample you have, it is at the same temperature throughout it. Right? So this is called equilibrium. Right? So in this situation, if N is the concentration, the number of electrons per unit volume, right? Then we will write this as in the conduction band, right? What is the number of, we said, electrons at some temperature, right? Electrons will have moved to the conduction band. So there will be some number of electrons in the conduction band, some number of holes in the conduction band. Now we are talking about the electrons in the conduction band. So if N is the number of electrons in the conduction band, I will multiply it with the density of states in the conduction band, right? And the function which gives you the probability of occupation. How much is the occupation of a single state? So that will give me the total concentration of electrons, right? Now, if I want to know how much is the number of electrons in the whole band, I have to integrate this. I have to integrate this equation from the energy. From here, EC, you know, there is conduction band here, and it goes to higher energies. There is valence band, it goes to lower energies, right? So I have to integrate this from EC, right, to some energy, whatever is the limit of upper limit, right? So the equilibrium electron in the conduction band. Right? If I call it N naught, the equilibrium electrons, right? Then I will integrate GC or function of the energy, right? And Fermi-Dirac probability, function of the energy, and to dE, right? And from the lower limit is C2. Some energy up high, but I can extend the limit to infinity because आप energy ऊपर जाए तो probability of occupation of electron becomes 0. So it will not make any problem if you extend the limit to infinity energy, right? It will not make a change. It will not make a difference. So you can write the upper limit as infinity, right? So I have to find this. If this is equation number 1, right? So I can put this GC here, from here, and f of e from here. Put this from here and put this from here, right? So what I get will be something like is equal to, right, this thing, putting this thing here. So that will be, should I write the whole thing or not, right? Okay. Let me go back to that. Let me go back to approximation for Fermi-Dirac. Approximation for Fermi-Dirac to Boltzmann. Right? A temperature greater than, right, 0, a temperature greater than 0, right, and at higher energy, so that E minus EF is greater than KT, right, E minus EF is very, very greater than KT, and that limit, right? So in that limit, I can approximate this thing, you know, sometimes we can omit 1 plus billion, 1 plus a billion is approximately equal to a billion. So this is a very big quantity. So we can approximate this by only this denominator, right? So we can write the Fermi-Dirac distribution as a Boltzmann distribution, right? When this is the situation, E minus EF is very, very greater than KT. So I will write this thing here. I will replace this with the Boltzmann distribution, and f, the Fermi function, will be approximately equal to e to the power E minus EF over KT, right? So I can now write, with the help of this, I can write equation number 2 is this. Oh, I forgot one negative sign. Because this 1 plus exponential E minus EF over KT, you just substitute this with just this, like you remove this, right? With the approximation, you can think of this like that, right? When you approximate this, then this is equal to this thing, because that is e to the power minus, right? Okay, now n naught can be written as, right, 4 pi to Mn, where Mn is the effective mass of electrons, right? Stop. To Mn, and KT, right? Divided by HQ e to the power minus, right? Let me, before doing this, I I was skipping one step and then I have to write many. I was skipping one, trying to skip one step, and then I have to put too many. Let me write that. Okay, n naught is equal to 4 pi or n squared cube and to 2 n star power 3 by 2, right? From EC to infinity and E minus EC e to the power minus E minus EF over KT and to GE, right? Now,
सर सर दरमियान वाला बोर्ड नजर आ रहा है, हाफ नहीं आ रहा, साइड पे नजर नहीं आ रहा, लेफ्ट साइड और राइट साइड पे.
बेटा that will be problem with you. मेरे पास तो ठीक है. That will be problem in your video setup. I don't think that is that problem with everybody. Are you using? Probably it's because you are using your cell phone. Maybe it's because you are using your cell phone, and cell phone has a different format than a laptop screen. So that's why you will not be seeing this properly. Anybody who is using a laptop?
यस सर, क्लियर है, बिल्कुल ठीक है सर.
Yeah, so it is clear. Those people who are using your cell phones, there will be problem if because you will have a portrait format in your cell phones for video. That is why it's not visible to you. Okay. Now, I know to do that, right? Let me put a substitution so that this integral becomes easier, right? Let me put a substitution, and the substitution is let E minus EC, right, divided by KT is equal to eta. Let me write E minus EC divided by KT is equal to eta, right? So when I do this substitution, right, then I can write n naught is equal to 4 pi 2 mn star kt 3 by 2 h cube, right, exponential minus EC minus EF over KT and integral, right? So this will be replaced by KT into eta, this thing, KT into eta, and that KT comes here, right? So you will get eta, right? And to e to the power minus eta d eta. When you do this substitution, right? E minus EC over that. Okay. That is equation number 3, right? Okay, this thing is your gamma function, right? And that was equal to, in your mathematics, that was equal to I square divided by 2. So I can write N naught is equal to 2 into 2 pi N N star divided by H square 3 by 2 e to the power minus EC minus EF over KT, right? That is a constant, right? 2 and 2 pi m, and all this is a constant, right? So I can write this is equal to NC e to the power minus EC minus EF over KT now. This is, look, N naught, the concentration, the equilibrium concentration of electrons in the conduction band is proportional to the difference between the conduction band bottom, right? If we look only at this equation, right, the concentration of electrons in the conduction band is equal to the difference between the bottom of the conduction band energy and the Fermi level energy, right? That is proportional to this, the exponential of, right? The exponential of the negative of EC minus EF over KT at a certain temperature. And this is called the effective density of states, right? We call this is the effective, this is a constant which is equal to this thing, which depends upon the effective mass of electrons, right? So we call NC is equal to 2 pi, right? N star over H squared 3 by 2 is equal to the effective density of states. we said that the Fermi levels, right? We through that later, at the end of this topic, we will show where is the position of the Fermi level, right? And we call this intrinsic semiconductors. Intrinsic semiconductors, semiconductors which are pure, which do not have any impurities, which do not have any defects. So we say that the number of electrons and the number of holes and them will be equal, right? So let us now find the concentration of holes in the valence band. We call the equilibrium concentration of holes, right? It is a function of the temperature as well, right? And it is a function of the difference between the conduction band bottom energy and the Fermi level. What is the difference between them, right? Now we want to find the concentration of holes in the valence band. Valence band, what is the concentration? How many particles, how many charge carriers are per unit volume in the valence band, right? So for that, we will write the distribution of holes, right, in the valence band, right? We can write them as G of V, density of the, right, density of states in the valence band, right? And look, if we want to find the concentration of holes, right? So we will say if the probability of occupation is F, then the probability of non-occupation is, then the probability of non-occupation, right? That is 1 minus F. So if we want to find the concentration of holes, it will be equal to the density of states. यानी इस हाल में कितने chairs हैं? And what is the probability of emptiness? Because we are interested in calculating the number of holes, empty chairs, as you know, as I usually give you the example of chairs in a hall. So that will be the density of states, which will be equivalent to the chairs, the density of chairs, multiplied by the probability of emptiness. And the probability of emptiness will be 1 minus the probability of occupation, right? So we can write this 1 minus F of F. So the distribution of holes in the valence band can be written is like this multiplied by this thing, right? So if I want to find the equilibrium concentration of holes in the valence band, right, P naught, then I should integrate, right, it for the valence band energy, right? So that will be GV into 1 minus F into dA, right? Now, look, I have to put this thing, I know this value, but why is this? Right? You remember the probability of occupation function. If you remember, if that is energy, right? If that is energy, and that is the probability of occupation, right? So if you remember, it was 1 until the Fermi energy at 0. And if you remember, at any temperature, the Fermi energy would lie with the probability of the Fermi energy occupation was half. So there was a curve like this. Right? And this was the Fermi energy. The probability of occupation of energy smaller than the Fermi energy is equal to 1. When you get closer to the Fermi energy, the probability of occupation gets smaller and smaller and smaller. And when you go a little above the Fermi energy, the probability of occupation is equal to 0. Right? Similarly, we said that the probability of emptiness, the probability not to be occupied, right, are 1 minus f. If this is f, this is the function f, right? The function 1 minus f. So this is f is equal to 1 here. So 1 minus f, 1 minus 1 will be equal to 0. So it will be 0 here. And it will be like this. So this is a function 1 minus f, right? 1 minus 1. This is 1 here. 1 minus 1 is equal to 0. So 0 here, then when this decreases, then this increases because it is 1 minus this thing. So this will increase. If you look at this, the Fermi energy, this curve f and 1 minus f are symmetrical. They are like each other, right? So f for energies, right, above the conduction band, right, that is like above the Fermi level, that is the function is the same. It was that Fermi-Dirac distribution, right? Fermi-Dirac, which we approximated with the Boltzmann distribution. So above the Fermi level, for energies E minus DEF are for energies above the Fermi level, right? EF plus DE for the energies above the Fermi level, EF plus any energy. It is F is equal to 1 over 1 plus e to the power, right? E minus EF over KT. But here, for below the Fermi level, 1 minus F is like that. So for energies, right, EF minus DE, right? For energies EF minus DE, the below the Fermi level, 1 minus F is like F. So the Fermi function is like the 1 minus F function. So we can replace 1 minus F with that, right? So 1 minus F here will be equal to, right, 1 over 1 plus E, right, EF minus E over KT. The Fermi-Dirac distribution function for energy levels below the Fermi energy, right, below the middle. That was in the other diagram, there was the Fermi level in the middle. So below the Fermi level, right? We suppose that the Fermi level should be roughly, it has a half probability. It should be roughly about the middle of the Fermi energy, in the middle of the conduction band and the valence band, right? Roughly. Okay, so 1 minus F is equal to this thing. And we put that GV, the density of state, which we gave it in the start of the lecture. Put that here and this here, and approximating this by Boltzmann distribution. So that will be 1 minus F will be equal to e to the power minus, because we are approximating this now with Boltzmann statistics, right? So we get T is equal to now, P naught will be equal to GV, right? And 1 over 1 plus e to the power EF minus E over KT, right, into DE. Now, ionize the value, right, from minus infinity to EV, right? The integration limits are from minus infinity because we are going below the valence band. So the upper limit is the valence band and the lower limit is the minus infinity. We are going from the bottom. We are going from the bottom. इसी कुएं के अंदर से हम ऊपर जमीन तक आना चाहते हैं, right? So it will be 4 pi, right, and 2 MP star divided by S squared 3 by 2, right? And it was EV minus E and e to the power minus EF minus E. It is the same thing as we did before. It's the same treatment, right? Now let us do a substitution. Substitution, right? What substitution? We want to put eta star is equal to E V minus E, right, over KT. Let us put this substitution, right? DE will be equal to minus KT into eta bar, right? Then this equation 3 now becomes, with this substitution, right? 3 naught is equal to minus 4 pi 2 MP and to star divided by n squared 3 by 2 e to the power minus EF minus EV, and there's a KT as well, KT. Over KT, and from infinity, right, to 0, eta prime square root e to the power minus eta prime d eta prime. Right? Look, it is minus infinity. Integral is from minus infinity. But now here, dE, when we do the substitution, dE becomes negative. So this turns the limit from minus infinity to plus infinity if we put this thing. If we do the substitution, we have to look for the limits as well, right? So the limit for energy is what? D. I forgot D here. So the limit for energy is minus infinity, right? But here the value of dE after the substitution is negative. So minus infinity will become plus infinity after the substitution, right? And there is a minus sign here with the substitution, right? So now we can do another step now. We can invert the limits, right? We can make this from 0 to infinity, but then we should multiply with a negative sign, with -1, right? We should multiply with -1. So that -1, when we change the limits, that -1 and this minus will multiply with each other, and that will become positive. Now, this Neaman function, right, from 0 to infinity, eta prime e to the power minus eta prime d eta prime is equal to square root of pi divided by 2. So when I put it there, P naught will become, right, 2. And I will put pi there, right? So it will be pi MP star KT, right? Divided by h cut square 3 by 2 e to the power minus EF minus E V over KT, right? R, the equilibrium distribution of holes is equal to, right, 2. Okay, let me write this as NV as before. NV e to the power minus EF minus EV divided by KT. This is equation number. What is the equation number? You should find out what was that equation number, right? Where NV is equal to 2 and 2. There is a 2 pi here. 2 pi, right? 2 pi MP star and KT divided by h cut squared 2 by 2. That is equal to effective density of states in the valence band, right? Effective density of states in the valence band, right? So we got the concentration of equilibrium concentration of electrons, right, in the conduction band, and the equilibrium concentration of holes in the conduction band. The equilibrium concentration of holes in the conduction band, P naught, is directly proportional to the exponential of minus EF minus EV divided by KT. It is a function of temperature and it is a function of the difference of Fermi energy and the valence band maximum. EV is the valence band maximum. Right? And now, if we call them as intrinsic semiconductors in equilibrium, right? No intrinsic semiconductors, intrinsic semiconductors. No doping, no impurities, no impurities, no impurities, no defects. No defects. Then the equilibrium concentration of electrons, we will call that Ni. Ni, intrinsic carrier concentration. Intrinsic, बगैर किसी मिलावट के, there is no मिलावट, right? खालिस सेमीकंडक्टर, उनमें चार्ज इलेक्ट्रॉन की कैरियर कंसंट्रेशन उनकी कैसी होगी, right? So that will be, I will change that N naught and P naught to Ni and Pi. Now I call them intrinsic for intrinsic, and still they are in equilibrium. Right? There is no potential difference applied. There is no change in temperature from one end to the other. Right? So I call it Ni. So it is equal to Nc e to the power minus, right? Is was Ec minus Ef divided by At. And Pi is equal to Nv, this is right? Nv e to the power minus and Ef is above that. Ef minus Ev divided by H. So these are the concentration of electrons in holes. Concentration means the number per unit volume. एक छोटे से वॉल्यूम में पर सेंटीमीटर क्यूब आपके पास कितने इलेक्ट्रॉन्स हैं, कितने होल्स हैं, that is given by this thing, where this contains what? It contains just the effective mass and the temperature, along with the Boltzmann constant and the Planck constant. You can get this from the effective mass of electron, right here. The effective mass of holes for the holes and the effective mass of the holes, K, the Boltzmann constant, the temperature, and the H comes to the Planck constant. This is effective density of states function, right? For conduction band, for the valence band. This is the effective density of states function for the conduction band, right? Okay. Now, there are examples in the book. You should solve those examples, okay? You should solve those examples. Now, if we multiply, right, these two equations, so we get Ni Pi is equal to NC into NV e to the power minus EC minus EF divided by KT e to the power minus EF minus EV divided by KT, right? R and C and V, right? And here is plus EF, here is minus EF. So plus EF minus EF would be 2, and that would be EC minus EV divided by KT, right? Or in the intrinsic case, जिसमें कोई आपके पास there is no doping, right? So when there is no doping, we say Ni will be equal to Pi. जितने number of electrons है, इतने number of holes हैं, right? Electrons conduction band में कहाँ से आ गए? इसी valence band से चले गए हैं. तो valence band में they have created an empty state. That is called hole. So Ni is equal to Pi. Ni is equal to Pi. Therefore, this can be written as Ni square is equal to Nc and V e to the power minus, and look, what is this thing? EC minus EV, right? आपके पास this is what? ये आपके पास EC है, and this is आपके पास EV है, right? The difference of the conduction band bottom and the valence band top. That is the valence band. And that is the conduction band. So इसके bottom और ये क्या है? That is EC minus EV, and that is equal to band gap energy. Band gap energy. How much energy is the gap? आपको V वैलेंस बैंड से जाने के लिए, अगर आप कंडक्शन बैंड में जाएं, तो आपके लिए कितनी एनर्जी दरकार है? That is that band gap energy. So Eg, right? So we call it Eg. Divided by Eg. Right? So that is an important equation, and we can find the intrinsic carrier concentration from here. If we know the band gap energy, right? If we know the band gap energy, we know the Boltzmann constant, we know the temperature, right? We know NC. NC is again, we get it from the effective mass of the electron, and the Boltzmann constant, the temperature, and the Planck constant. So if we know that, we get NC. Similarly, we know the constants for the valence band density of states function. So we can get from this equation, right? From this equation, we get what? We get the intrinsic carrier concentration. Remember, Ni is equal to Pi, the number in intrinsic case. Khalis case में, pure case में, number of electrons will be equal to the number of holes. So if you know the number of electrons, that is enough, because the number of holes is equal to the number of electrons, right? So this equation is an important equation through which we can find the number of or the concentration of electrons in holes in a semiconductor, right? Okay. I believe this is sufficient for today because you have to catch up with your previous work, and we should stop here. If there are questions, you can ask. Do you want to ask any questions?
सर जी ये लेक्चर अगर आप ग्रुप में शेयर करें तो हम सारे लिखेंगे, वैसे यहाँ से तो लिखना मुमकिन ही नहीं था, नजर नहीं आ रहा था
That
ठीक
is
से।
not. I will not guarantee that. That's a lot of work. I have to download this. It takes hours and hours. I have to download this, and then I have to. If I have to upload it, it will take hours and hours. So I cannot promise that. I may try, but I will not promise about that. I can try, but it takes a lot of time to download this video and then to upload that video. This will take a lot of time. So I will try sometimes, but I cannot promise that.
और
And
सर
if
रिकमेंडेड बुक कौन सा है?
sorry,
सर बुक सर
you
रिकमेंडेड
already
बुक
know
जो है
about the book because we discussed it in the first lecture. That is the Semiconductor Physics and Devices by Neaman, and I had sent it to everybody. It's available on the internet as well, but मेरा तो ख्याल था that it is our because this was the very first lecture when I was talking about having a book, and you have it in your soft form in the soft format. So it is Semiconductor Physics by Neaman, Semiconductor Physics and Devices, and that was we discussed it in the very first lecture. So if you do not have it, either you should email me or you can email Tahir or me. I have it and he might have it. All the students should, in principle, must have it, must have the book. I don't know how can you pass the course without having a book. So if there is no question, I should stop and what should be